Okay, Assalamu alaikum. So this is our module 2, week 6 lecture, part 1. Today we are going to talk about multiple and single cycle computers. We said the single cycle computer which we studied in week number 5, it was a good computer. However, it has some shortcomings. These shortcomings include the complexity of instructions. A single cycle is limited. We saw that these instructions are quite simple instructions. Accessing both instructions and data from a single cycle memory is quite impossible. We cannot access both the memory and the instruction memory and the data memory at the same time. A long worst case delay path limits the clock frequency and the rate of performing the instructions. So this we will talk about in pipelining. However, the first two shortcomings, which are these shortcomings, we are going to address in this class over here. So first of all, we need to convert our single cycle computer into a multiple cycle computer. Multiple cycle computer means the instruction will go multiple times within will pass through the data path multiple times in order to execute one instruction. Sorry. So first of all, we need to modify the data path and memory, and we need to modify the control unit. Then we need to design a multiple cycle hardwired control. So the block diagram of the single cycle architecture is given over here. So this is our multiple cycle computer. You can see that a few things has changed. If we look, we can start from our register file. Our previous register file was 8 by 16. Now it is 16 by 16. So we have 16 registers instead of 8 registers. Now changing from 8 to 16 means the address will go from 3 to 4. But remember we need to still accommodate our previous instructions which have 3 to 3. So we have here an address register logic which will convert the inputs from 3 to 4 depending on the instructions. And now we can see the AX, BX, DX which we are used to in assembly language. Now we can have them over here as AX, BX, and DX. So these are coming from our control logic over here, but our original instruction will have the normal DR, SA, and SP. Basically, we want to accommodate the previous instructions which were discussed in the previous week and add to them complex instructions. So the data set, we are not going to scrap the data set from the beginning. We are going to build upon it. So we need to have support for the new instructions. So the function unit is still most likely the same. The VC and Z are also going over here to the control logic. We have the memory, which is now memory M over here, and this is our instruction register. Now we are going to a more conventional Van Neumann architecture in which we have one memory, as you can see, and the memory will have either the output for data N or another output, which I'm going to draw in green. This output is going to our program counter. Okay, this output will go to the instruction register and the program counter and so on. So basically one memory, and we are trying to do all of these are complex to implement complex instructions. So first of all, we are going to talk about the modifications in the data path. So it's not essential to use multiple cycle design, but it is done to illustrate the concept where the modifications are done. It requires a new multiplexer M, which will choose between the inputs. Are we going to take an input from bus A, or are we going to take an input from the program counter? Are we going to take it from the program counter or from mux A? So because we are using only one memory, okay? Because we are using only one memory. So see here we use a single memory for both. However, it's not essential, but it is done for illustrating the concept. Then it requires an output over here, which I have already talked about. Over here you have an output going back into the, I don't want to keep the colors, let's change the color. We have an output going from here into the instruction register. So previously we had the memory over here, the program counter will go here, and this one will go here. Now we have only one memory, just for the illustration of the von Neumann architecture concept. Previously we were working on the Harvard architecture concept. So this is our memory line as described earlier. Now the modifications to hold the operands between cycles. Of course, we are going to need additional registers. So now you can see we have a 16 by 16 register file, and the bits will go from 3 to 4. So the register file will have normal registers from 0 to 7 and temporary registers from 8 to 15. So the control word will specify which one of these we are going to use. The new registers, which are AX, BX, and DX. And these are illustrated over here. This is our new MUX-M. This is our register file, which is 16 by 16. This is our register logic that will implement all of this together. So the control unit modifications, as you can see here, the control unit, we have a state control part. We have the control logic changed a little bit, and we have the PS here indicating to the program counter what exactly to do, and PS is the sequence control. Okay, so basically it's more or less minor changes. So here it requires an instruction register to hold the registers between memories. So we have the instruction register over here. IL is the instruction load. If we are going to load a new instruction or not depends on IL, and IL you get it over here from the sequence and control part. It requires a hold for the program counter. So the program counter has a hold option, which is controlled by PS. And the new encoding of the program counter operates on 2 bits, as we are going to see. See here we have an hold operation, and this is the instruction register that we were talking about. So now we have the program counter, we have the instruction register, we have AX, we have BX, we have DX, the same things that we studied in microprocessor previously in level 3. So the sequential control is used in order to control the micro operations of multiple cycles. Remember, the instruction will pass through the data path multiple times for one instruction. So we need to know the input, which is the opcode and the status bits over here. The input, which is the opcode, let me clear this one, which is the opcode over here, plus the status bits, which are, sorry, these 4 over here. You can see these are the status bits, and you need the next state, which is coming from the control state. Okay, so the next slide we are going to talk about the registers to store the control state and the combination logic to generate this control word. And the combinational logic is quite complex, so usually we use a PLA, which is a programmable logic array. So this will be used in our design for the control logic, not a simple logic gates like we did earlier in the single cycle computer. So this is our control word now. Our control word, we will go from 0 to 28 bits. These are normal data path for a normal instruction. If it's a single cycle instruction, we are going to use these normal bits, which we used earlier, MW, MM. The only extra bit, previously it was 20, now it's 21 because we have MM added to our memory. Extra, we have instruction load, which is 1 bit, PS, which is 2 bit, and next state, which is 4 bits. These are all added for our instruction, for our sequencing part. So we have instruction load, program counter select, and we have the next state, which is 16 bits. These next state give us for each instruction a possibility of 16 states that can be used. So your instruction can have a maximum of 16 paths within the data path. So encoding all of this together, you can see that we have the data path as a usual data path over here, where we have these 4 bits. If the first one is 0, and these are 3 x's, so we start with 0, 0, 0 for R0, 1, 0, 0 for R1 until 1, 1, 1 for R7. If now we have from 1 up to F, we have, or 15, we have, these are the temporary storage, MB more or less the same, 0 for register, 1 for constant, function select are all the same, the coding for all the function selects are over here, MD, function unit or data n, RW, MD, and ROut are all the same. So basically this is the end of our first part. In the second part we are going to continue and have some examples on multiple cycle computers.